This presentation is delivered by the Stanford Center for Professional Development.
No. Okay. Big day today. Big day, big day. It's finally time to reap some of the benefits of the discussion, rather general, and I think it's fair to say, abstract discussion we've been having. May still seem a little abstract to you today, I understand that, so just ride along, all right? And you'll see today some amazing formulas that come out of this effortlessly in finding the Fourier transform of some well-known functions, things we're really going to have to use. It's really just, I don't know, just a pocket full of miracles, and the fun never stops. So I want to talk today about the Fourier transform of a generalized function or a distribution, also known as a distribution. Fourier transform of a distribution. So let me remind you, first of all, what the setup is, what goes into this. To define a distribution, you need first of all, a class of test functions. So the setup is you first have to define a class of test functions or test signals that usually have particularly nice properties for the given problem at hand. And it can vary from problem to problem. For us, for the Fourier transform, it's the class of rapidly decreasing functions. So these typically have particularly nice properties. Sorry for not specifying that terribly carefully. But they come generally out of, again, sort of years of bitter experience with working with problems, working with a particular class of applications, and trying to decide what the best functions are for the given class. For Fourier transforms, for the Fourier transform, the class of test functions is the rapidly decreasing function. So I won't write down the definition again, but I'll remind you of the main properties in just a minute when we need it. Rapidly decreasing functions. These are the functions which are infinitely differentiable, and any derivative decreases faster than any power of x. So they are just as nice as you could be. Rapidly decreasing functions. All right, that's what you need. You need a class of test functions. And then by definition, a distribution or a generalized function is, to use the most compact terminology, a continuous linear functional on the set of test functions. Distribution, also called a generalized function. This term is probably not used, generalized function is probably not used as much as it once was when the subject was new. Nowadays people just call it distribution, since Schwartz is really unifying work on all this. So let me give you the shorthand notation for this. A continuous linear functional on test functions. All right, so that means it satisfies two properties. So you write the pairing if phi is a test function and t is a distribution. We will write most of the time, but not always, t phi with that sort of pairing for t operating on phi. All right. So if you want, you can think of phi as some distribution of physical information, temperature, voltage, current, whatever, and t is a way of measuring it. All right. So you measure something and you get a number. All right. So t is a measuring device, and phi is the thing you are measuring. So t operates on phi in such a way that it satisfies the principle of superposition, or that is to say it's linear, and it's also continuous. So t is linear, meaning t of phi1 plus phi2 is the same thing as t operating on phi1. I'll write it up here. T operating on phi1 plus t operating on phi2. And the same thing for scaling. So t operating on alpha times phi is alpha operating on t of phi. That's the property of linearity. And the property of continuity can be phrased in different ways, but the most direct way of writing it, and I'll have a comment about this in just a second, is that if phi n converges to phi, a sequence of test functions converging to a test function phi, that implies that the measurements of phi n also converge to the measurement of the final test function. So really there's nothing wrong with trying to impart sort of a physical interpretation, but I don't want to try to push that too far. But again, you think of phi as some sort of something to be measured, and t is the thing that does the measuring. Now, I want to make a comment about the mathematical, one quick comment about the mathematical foundation for this. The hard work in all of this is this statement right here. Phi n converges to phi. All right, the hard mathematical work is to define phi n converging to phi. What that means. Because these space of functions, although each individual function has particularly nice properties, infinitely differentiable, all the derivatives decay, and so on and so on, if you want to talk about a sequence of functions converging, then the more you insist on, the more properties you insist the function having, the harder it is to control the sort of convergence. You know, if the function is infinitely differentiable, then you want all the derivatives also to converge. If the function is rapidly decreasing, you want all the derivatives to be rapidly decreasing, and so on. So it's hard to write conditions down that are going to control this. That's what's difficult to do. And if you open a math, this is a warning, if you open a math book that says something like theory of distributions or theory of generalized functions, it's going to be like the first 100 pages or so are going to be devoted to analyzing what it means to say that phi n converges to phi. And you look at that and you say, why would anybody learn this subject? And I wouldn't blame you for saying that. All right? It's complicated. There's no two ways about it. If you're going to give a very, very precise treatment of it, then you really have to do that. We don't have to do that. All right? I'm going to take this sort of, again, as intuitive as you can make that. Imagine controlling the functions, all the derivatives, and so you can think in terms of the graphs. The graphs of phi n converge to the graph of phi, and everything is controlled as nicely as you want. So suffice it to say, it can be defined precisely, but that's not for us to do. All right, but I did want to point that out. The other bit of terminology here, for those of you who have seen this, for those of you who have studied a certain amount of extra math, in particular the field that's usually called functional analysis, is that one says that the set of distributions is the dual space of the set of test functions. That's another way of phrasing this. So the distributions, the particular class of distributions that you're considering are the dual space the space of test functions. Bring that up at a cocktail party some night. Watch the people scatter. All right? Okay. Now, we had a couple of examples last time, and I want to remind you of that. The first example we had was delta defined as a distribution, and it's the simplest distribution. This mysterious delta function that's supposed to capture this property of concentration at a point emerges as simply evaluation. All right, so examples. Delta. All right, so delta as a distribution is defined simply by delta operating on phi is phi of 0. All right? This replaces, now that's a pairing. Once again, in all this, what you're going to hear me say a lot today is, I'm going to define a distribution. What does that mean? That means you give me a test function, I have to tell you how to operate on it. All right? So you give me a test function phi. To define a distribution, I have to tell you how that distribution operates on phi. So I say, how does delta operate on phi? Delta operating on phi is just phi of 0. Nothing else. Period. All right? This makes precise. This dispenses with all of that bullshit about the classical definition of delta. It's 0 everywhere except at one point where it's infinity, and the integral is 1, and so on and so on. All that is gone. All that is swept aside by this definition. Now, it took a while to get to that definition, okay, but once it's there, that's what you can work with. Okay? Likewise, there's the shifted delta. I call it delta sub A, and that's just defined by, so again, to define a distribution, you give me a test function, I have to tell you how it's defined. I have to tell you how it operates. And I say delta A operating on phi is phi of A. Period. Period. Okay. Now, I would be remiss if I didn't indicate, there's a graphical way of picturing these deltas, all right? So the graphical picture, and we'll use this too. You usually indicate the delta function by a spike at the origin, delta, all right? And since it's supposed to have infinite height, I can't exactly draw an infinite spike. So I just put a little arrow there. Everybody writes it like this. All right? And likewise, delta sub A is usually indicated by a spike at A. Okay? Now something else. All right? Since we've been so careful about this, and since I've made such a big deal out of the fact that it's all airtight and we can dispense with integrals and things like that, I am not going to blame you, and I'm not going to try to drive out of your system expressions like this. Integral from minus infinity to infinity of delta of x, phi of x, dx is equal to phi of 0. If you want to write that, okay. I'll even write it from time to time. It's okay. Nothing bad will happen to you. All right? Among friends, it's perfectly okay. And a corresponding thing with a shifted delta function. It's all right. All I want you to be aware of is that one can, this is just really a mnemonic in some sense. This is in some way a more complicated way of writing that. All right? But in some formulas and in some contexts, it's helpful to write that. And okay, all right, do not be afraid now that you have the hidden knowledge, all right, of what's really going on, because this is what's really going on. The second example we had of distribution was really an example of a whole class of distributions, and that was by way of assuring us that nothing has been lost. All right, now these things are sometimes called, as I said, generalized functions. So if they're generalized functions, they ought to include the original functions, the good old functions. And they do. That is the second example. I say a class of examples are really distributions induced by, this is probably the best way of saying it, induced by functions. All right? So if f of x is a function such that I can integrate it against the test function such that this integral, minus infinity to infinity, say f of x, phi of x, dx, makes sense, the integral converges. All right, and that will be the case for many functions because phi is such a nice function, phi may be such a nice function that even if f is a bad function, the product is going to be such that the integral converges. All right, if that makes sense, then that's a number after all. I integrate f of x against phi of x, and that's linear because the sum of the integral is the integral of the sum and so on. And it's also continuous. That's a little harder to show. And so that defines f. That defines a pairing of f and phi. Continuous. Again, I'm not going to show that. A pairing of f and phi. In that sense, f defines or induces a distribution. You give me a test function, I have to tell you how the distribution operates on it. How does it operate on it? It operates by that pairing. And so for shorthand, I write f paired with phi. What I'm really thinking of here is the distribution induced by f, but that's too many words. So f of x times phi of x dx. Okay? So a lot of functions which are not as nice as the test functions are included in the set of distributions instead of things that operate on test functions. So for example, it may be the case that 1 pairs with phi. So this includes many functions. Many functions induce distributions. So it can be regarded as distributions. So e.g., it may be the case that integral of 1 minus infinity to infinity phi of x dx, which is the integral from minus infinity to infinity of 1 times phi of x dx, that may make sense. It should make sense. You don't want a function which is not integrable, for goodness sakes. And so in that sense, 1 induces a distribution because I can allow 1 to operate on phi by means of this integral. Okay? And likewise, sines and cosines are not themselves integrable, but if I multiply them by a function which is really dropping down, which is decreasing at plus or minus infinity, then the integral of sine or cosine against such a function will make sense. And in that sense, sine and cosine can be considered as distributions, that is, they operate them. So let me, just for short, the complex exponential often works. So e to the 2 pi I ax might be okay, provided the integral from minus infinity to infinity, e to the 2 pi I ax phi of x dx makes sense. Which for many functions it will. Okay, it will. Even though e to the 2 pi I ax itself is not integrable, if I multiply it by a function which is decreasing, the product will be integrable, say. All right? So that induces a distribution. How does it operate on the function? It operates on the function by integration. Okay? All right. And if you look at this example and if you think of a Fourier transform coming in, you wouldn't be too far off, because now the big moment has arrived where I'm going to define the Fourier transform of a distribution. So we've talked about distributions and the definition of distributions and a couple of examples of distributions. I want to do something with them. And this is so cool how this works, I think. So again, just enjoy the ride. All right, and watch how these derivations go. It's almost effortless the way this all works. I mean, it's just so, it's better than sex. Not that I would know, I was a math major, but. So I want to define the Fourier transform of a distribution. So now we're going to look, the test functions we're going to look at now are the Schwartz functions, the rapidly decreasing functions. So let's take the test functions to be S, the rapidly decreasing functions. All right? Now let me remind you of why they are so good for Fourier transforms. All right, why they are so good for Fourier transforms is if phi is in S, then so is its Fourier transform. All right, and for that matter, I guess I don't think I said this, but for that matter, the inverse Fourier transform is also in S. Okay, inverse Fourier transform differs from the Fourier transform only by a minus sign, so if one isn't there, it's easy to see the other one is. So that's one property, and the second is that Fourier inversion works. All right. It is in that sense, those sense, let me write the second one down. That's the first property is that the function is rapidly decreasing, so is its Fourier transform. Second is that the inverse Fourier transform of the Fourier transform of phi is equal to phi, and likewise the Fourier transform of the inverse Fourier transform of phi is equal to phi. Those are the properties that make phi the right class, the best class of the classical functions to use when you want to talk about the Fourier transform. The classical Fourier transform is defined by the integral. All right? So these are the functions we're going to use. The corresponding class of distributions is sometimes called the class of tempered distributions. Of distributions are called the tempered distributions. All right? And what I want to do now is I want to show you how to define the Fourier transform of a tempered distribution to be another tempered distribution. Okay? If T is a tempered distribution, I want to define its Fourier transform. And this will be another tempered distribution. Okay. Now again, you will hear me say over and over again today, I want to define a distribution. What does that mean? That means you give me a test function, I have to tell you how it operates. So I have to tell you how to define the Fourier transform, something I'm going to call the Fourier transform of T operating on phi or paired with phi. So I have to define the Fourier transform of T operating on phi, where phi is a test function, rapidly decreasing function. How shall I do it? How shall I do it? All right. There is a guide in this. There is a guide in all things, all questions of this type. You want to know how you should define an operation on a distribution. you ask yourself, you start off by asking yourself, what would I do if I were in a really good situation here? Like if f of t were itself a rapidly decreasing function, say, or some other good function, and this pairing was by integration. All right, so what if? This is another example of suppose the problem is solved and see what has to happen. All right, so what if the pairing is by integration? It may not be in general, okay? I mean, delta doesn't arise by integration, but suppose it does arise by integration, what would the formula, where would I be led? Where would I be led? So suppose that everything works out as smoothly as possible. What are the consequences of that? All right, so let's say that the Fourier transform paired with phi is the integral from minus infinity to infinity of the Fourier transform of t of x, phi of x, dx. All right, so again, this would not be necessarily the case in general because a distribution is not always given by integration, but suppose it is. And what has to happen? All right, so suppose, then again, I'm supposing that everything nice is happening, so the Fourier transform is given by an integral. It's the integral from minus infinity to infinity. I've already used x here, so let me write this, minus 2 pi I xy t of y dy, then times f of x dx. Supposing that I can do this. All right, supposing that everything is nice enough that I can do that. All right. Then, all right, you buy the premise, you have to buy the gag, you have to follow your pencil all the way through and see where it leads you. So then I can combine all that. Let me write this as one big integral, minus infinity to infinity, minus infinity to infinity. Then I'm going to split it up again. So e to the minus 2 pi I xy t of y f of x dx dy. Or I guess I wrote a dy dx. Doesn't matter because now I'm going to split everything apart again. dy dx. All right, so now I'm going to swap the order of integration, and I'm going to put the f. Did I call it f or phi? Sorry. This is phi. This is phi. My apologies. Phi, and this is phi. Okay. So now I'm going to swap the order of integration. I'm going to put the phi with a complex exponential and leave the t alone. And write this as the integral from minus infinity to infinity, the integral from minus infinity to infinity, e to the minus 2 pi I xy, phi of x dx, and then the result is integrated against t of y dy. Now what is inside the integral here? Everything is as nice as it could possibly be, he said, bouncing up and down. So this is the integral, this is the Fourier transform of phi, evaluated at y, because I'm integrating e to the minus 2 pi xy phi of x dx. So this is the integral from minus infinity to infinity of the Fourier transform of phi at y times t of y dy. Okay? Where do we start? Where do we finish? We started with, supposing everything was as nice as it could be, and the pairing was given by integration, we had this expression, the Fourier transform of t paired with phi is the integral from minus infinity to infinity of t of y, the Fourier transform of phi y dy, and you have to look at this and look at this backwards in the sense that what appears here is the pairing of t and the Fourier transform of phi. All right? If everything is as nice as possible and the pairing is given by integration, then what has occurred by our following our trusty pencil is that this is the pairing of t with the Fourier transform of phi. Okay, so now you say to yourself, if everything were as nice as possible, how would I pair f of t with phi? What would the Fourier transform of t be paired with phi? It would be the same as if t were paired with the Fourier transform of phi. Okay? All right, now, this right-hand side is going to make sense regardless of what I did before I got to it. All right? Why? Because t is a tempered distribution. T operates on Schwartz functions. T operates on rapidly decreasing function. If phi is a rapidly decreasing function, so is its Fourier transform. That's the property of Schwartz functions. That's the property of rapidly decreasing functions. So it makes sense for t to operate on this. All right? This left-hand side may not have initially made sense, but this right-hand side will make sense. All right? Now, bless your souls. What is the thing to do? The thing to do is to turn the solution of the problem into a definition. All right? Turn this into a definition. Define the Fourier transform. So again, I'm telling you, so for a given distribution t, tempered distribution t, so t is a tempered distribution. I want to define the Fourier transform. I want to define a distribution. You give me a test function. I have to tell you how the distribution operates on that test function. I want to define the Fourier transform of t by how it operates on a test function. The Fourier transform of t operating on phi is, by definition, t operating on the Fourier transform of phi. On the right-hand side, this is the classical Fourier transform of phi, given by an integral, because phi is as nice a function as it can be. This is a new f, so to speak. This is a definition of the Fourier transform of the tempered distribution t. How do I define a distribution? You give me a test function, I have to tell you how it operates. It operates by t operating on the Fourier transform. And the right-hand side makes sense because if phi is a rapidly decreasing function, then so is f of phi. Wish I could smoke a quiet cigarette here. But I don't smoke. It's so cool. Now, look, you might say, what a cheat. I mean, what a cheat. I mean, you're telling me after all this that the Fourier transform of t operating on phi is t operating on the Fourier transform. That's what I'm telling you, and that's because I'm compelled to tell you that. All right? It has to work out that way if everything else is going to be consistent. All right? Now, how should we define the inverse Fourier transform? We define the Fourier transform. How shall we define the inverse Fourier transform? Of a distribution. Well, the inverse Fourier transform of t operating on phi must be nothing other than t operating on the inverse Fourier transform of phi. Okay? What else is it going to be? And now let's prove Fourier inversion. Fourier inversion would say the inverse Fourier transform of the Fourier transform of t is equal to t for any distribution. And also the Fourier transform, the inverse Fourier transform of t is equal to t. All right? It's the most important subject, it's the most important theorem in the field. All right, if you can't invert the transform, it's not going to do any good practically. So this is the most important of the theorem. And it's trivial. It's an absolute triviality. Why? Because everything has been carefully defined. It is a triviality because all the terms in this expression and how to operate with them have been precisely defined. What is the inverse Fourier transform of the Fourier transform of t operating on phi? The inverse Fourier transform of something is equal to the something Fourier transform applied to the inverse Fourier transform of phi. What is the Fourier transform of t operating on this test function, which is legit because the inverse Fourier transform is again a rapidly decreasing function? It is t operating on the inverse Fourier transform, it is t operating the Fourier transform of the inverse Fourier transform of phi. Fourier transform operating on something is the something operating on the Fourier transform. It's t operating on the Fourier transform of the inverse Fourier transform of phi. But in the space of functions which are as nice as possible for Fourier transforms, classical Fourier transforms, Fourier inversion works. So this is t operating on phi. Where did we start? Where did we finish? We have found that the inverse Fourier transform of the Fourier transform of t operating on phi is the same thing as t operating on phi for every test function phi, and therefore the inverse Fourier transform of the Fourier transform of t must be t. Period. The most important theorem in the subject emerges absolutely effortlessly because all the terms were properly defined. The calculation just took care of itself. All right? The effort to try to prove this in the classical case is just murder. All right? Is just murder. You can prove it in the case of Schwartz functions. You can prove it in the case of rapidly decreasing functions. And the proof actually is not in all detail, but in most of the details is given in the notes. All right? And there it goes pretty smoothly because the functions are as nice as possible. But if you try to start to prove Fourier inversion when the functions are not quite as nice as possible, you run into all sorts of mathematical snares. All right? But if you broaden your perspective, and that's what's really required here, if you broaden your perspective on this and let these new ideas in, then it becomes just a piece of cake. It becomes a deduction immediately from the definition. All right, now, let's have a Fourier transform hit parade. Let's calculate some Fourier transforms, because one of the things I said to you and I want to show you now in a way I hope you'll believe is that you can calculate with this definition. It's not just for proving theorems. It's not just for making things rigorous. It also provides you a way of calculating in a way that you can have greater confidence in your answers. Let's find the Fourier transform of delta. All right? The mysterious delta function. Now, trying to find the Fourier transform of that, I mean, my God, what could be harder in the classical case? But when you give the setup in terms of distributions, it is so simple. Watch. To define the Fourier transform of delta, by definition, the Fourier transform of delta operating on a function phi is delta operating on the Fourier transform of phi. That's the definition of the Fourier transform. Okay? You give me a test function, I have to tell you how it operates on the test function. The Fourier transform of delta operating on phi is by definition delta operating on the Fourier transform of phi. But now, how does delta operate on a test function? Delta operates on the test function by evaluating. That's the Fourier transform of phi evaluated at 0. Okay? But now, what is the Fourier transform of phi at 0? Now I write down the classical definition of the Fourier transform and evaluate it at 0. I can do that because phi is just as nice a function as it can be. This is, by definition, the integral from minus infinity to infinity of e to the minus 2 pi I 0 times x, phi of x, dx. In other words, it is the integral from minus infinity to infinity of 1 e to the 0, 1 times phi of x, dx. And now you have to look at this and have to look at it with new eyes. The integral from minus infinity to infinity of 1 times phi x is the function, the constant function 1 paired with phi. If I regard the constant function 1 as inducing a distribution, where do we start? Where do we finish? We found that the Fourier transform of delta paired with phi is the same thing as 1 paired with phi. And that is true for any test function phi, and therefore the Fourier transform of delta is equal to 1. The simplest of all distributions has the simplest of all Fourier transforms, the constant function, 1. The Fourier transform of delta is 1. Airtight. Airtight. All right? Now, you may very well have seen this in other classes. You may very well have seen other sort of tortured derivations of this property, that the Fourier transform of delta is 1. But this is the right derivation of this property. Okay? Nothing is in question here. Absolutely nothing. Now, you see how easily I could compute that? All right, I've got a certain amount of practice. It's true. But none of these steps was hard. And it's worth your effort to sort of go through and say these things to yourself out loud. Say them out loud. All right? Because it works so nicely and so easily. By the way, this is another example of, as a matter of fact, this may be the extreme example of the sort of dual relationship between concentrated in one domain and spread out in the other domain. All right? Delta is infinitely concentrated. All right? Sort of by definition, that's what delta is supposed to be. Delta is supposed to be the function, delta is supposed to be the limit of functions that are concentrating at a point. Its Fourier transform, 1 is uniformly spread out. Isn't that nice? That's the other thing you have to sort of say to yourself. Every time you have one, I mean, I know it's hard because there's so many little bits and pieces like this. But that's one of the things you start to get used to when you work in this subject for a while, when you use it, is you start to have these little checks. You know, these little interpretations that you carry with you from old situations to new situations. The old situation was, in the stretch theorem, concentration in the time domain means spreading out in the frequency domain, and vice versa. All right? So here, concentration in the time domain is spread out in the frequency domain in the most uniform, in the most extreme case. Let's do some more. What is the Fourier transform of delta sub A, the shifted delta function? All right. What about the shifted delta function, delta sub A? All right, what is the Fourier transform? The Fourier transform of delta sub A, I have to tell you how it operates on a test function. The Fourier transform of delta sub A is, by definition, delta sub A operating the Fourier transform of phi. But what is delta sub A operating on anything? It evaluates the thing at A. That is, this is the Fourier transform of phi at A. All right? What is the Fourier transform of phi at A? It is the integral from minus infinity to infinity, e to the minus 2 pi I ax phi of x dx. And now, again, you have to look at this with new eyes, and you have to say to yourself, this is the pairing of the complex exponential with phi. This is the pairing of e to the minus 2 pi I ax with phi. Where do we start? Where do we finish? We have the Fourier transform of delta sub A paired with phi is equal to e to the minus 2 pi I ax paired with phi. And therefore, that holds for every test function phi. That identifies the Fourier transform of delta sub A as e to the minus 2 pi I ax, where the right-hand side is understood as a distribution. Okay? It's the distribution which operates on a test function by this pairing. You may have seen this. You may have seen some tortured derivation of this too. But this is the right derivation of it. And while we're at it, why don't we find the Fourier transform of the exponential, complex exponential? Hey. Let's find the Fourier transform of, where is it here? Yes, let's find the Fourier transform of e to the 2 pi I ax. How do I do that? Where this is understood as a distribution. This would not exist in the classical case, right? I mean, you can't find the Fourier transform of this by computing the integral. But we can by pairing. The Fourier transform of e to the 2 pi I ax paired with phi is equal to, by definition, e to the 2 pi I ax paired with the Fourier transform of phi. That is the integral from minus infinity to infinity of, this is a function pairs with Fourier transform, e to the 2 pi I ax paired with the Fourier transform of phi, x dx. Now look at that, and what do you see? What do you see? What do you see? You see the inverse Fourier transform. This is e to the 2 pi I x times the Fourier transform of phi, classical Fourier transform. You are computing there the inverse Fourier transform evaluated at A. This is phi of A. because this is the classical inverse Fourier transform of the Fourier transform at A. So it is phi of A. But phi of A is the delta function at A paired with phi, if you use your new eyes. All right? So where do we start? Where do we finish? We started with that. We finished with that. The Fourier transform of e to the 2 pi I ax paired with phi is the same thing as delta sub A paired with phi. That identifies the Fourier transform of e to the 2 pi I ax as delta sub A. Airtight. No question. Take the particular case, actually, when A is equal to 0. Take the case when A is equal to 0. If A is equal to 0, I have the Fourier transform of 1, e to the 2 pi I 0. And what do I get? The Fourier transform of 1 is delta sub 0. The Fourier transform of delta is 1. The Fourier transform of 1 is delta. No doubt about it. No doubt about it. And again, this is a nice illustration of spread out in the time domain, concentrated in the frequency domain. Uniformly spread out in time, infinitely concentrated in frequency. Delta, concentrated, infinitely concentrated. All right? It works. It works great. Couple of more. How about, do it up here. Sines and cosines. Sines and cosines do not have classical Fourier transforms, but they have generalized Fourier transforms because sines and cosines make sense as distributions. All right? For instance, cosine of 2 pi ax. I'll stick with the sort of scaling by a. All right? That's easy to do because that's 1/2 e to the 2 pi I ax plus e to the minus 2 pi I ax. And I take the Fourier transform of each piece. So the Fourier transform of cosine of 2 pi ax is 1/2 the Fourier transform of this, which is delta sub a, plus the Fourier transform of this, which is delta minus a. I replace a by minus a in this expression, so it's delta sub minus a. Okay? So simple. So simple. Really. There's a graphical way of representing that. The graphical picture usually goes like this. You write it by two spikes, one at A and one at minus A. Here's 0. So this is usually people usually denote the Fourier transform graphically by this. And that's fine, that's fine. You can write it like that. The picture is that. How about the sine? The sine function is just as easy because the sine function can also be expressed in terms of complex exponentials. The imaginary part of the complex exponential. So the sine of 2 pi ax is 2 pi ax is 1/2I times e to the 2 pi I ax minus e to the minus 2 pi I ax. And so its Fourier transform, which I guess I'll do over here, is the difference of two delta functions times this complex number, 1/2I. Fourier transform of sine of 2 pi ax is 1/2I times delta sub a minus delta sub minus a. Nothing to it. Nothing to it. All right. Once again, I said a little while ago that the problem with the classical Fourier transform is that it didn't make sense on the functions that you really wanted to make sense on, like the functions that society needs. Trig functions, constant functions, and so on. All right? But now, if you open your mind and open your eyes, all those things work. All those things work, and it's effortless. It's effortless. Now, it takes some effort before it becomes this effortless. Yeah?
We have this more general framework. Is that also how you define the Fourier transform of classical functions that you could do before, like the rect function?
All right, so that's a good question. The question is, what happens to all that we did before? Now, honestly, to be the most honest and rigorous about this, you should always consider tempered distributions. So that is to say, if you want to take the Fourier transform of the rect function, all right, here's two ways of doing it. You can consider it classically. That's fine. There's nothing wrong with that. Or you can say the rect function induces a distribution, right? And its Fourier transform is the sinc function, also understood as a distribution. Now, that's going a little too far in some sense, in that, you know, when these functions are nice enough, when a function induces a distribution, you tend to blur the distinction between the function and the distribution that it induces. All right? But the most proper way of saying it is you only consider the Fourier transform for tempered distributions. That's where it's properly defined. And so classical functions, where we computed the Fourier transform before, should be understood as distributions, and everything should be in that framework. All right? But then you have to say to yourself, look, we're not kids here. Or, you know, we have to take a reasonable approach to this, and you don't want to abandon what you have done in the past. All right? So it's one of these things where you have to keep a little tension, a little cognitive dissonance, right, in your head between the Fourier transform on tempered distributions and the Fourier transform on a function when it does make sense. All right? So, and I'm going to make that blur. I'm going to blur that line. All right? That is, I'm going to write the Fourier transform of the rect function is the sinc function without worrying about it. All right? Without saying, really, it has to be distributions, it has to be understood in the sense of distributions, and so on. So, for example, when you write now, as a matter of fact, and I say this in the book, you can finally justify completely that the Fourier transform of the sinc function is the rect function, or the inverse Fourier transform of the sinc function is the rect function. Same thing. All right? You can do duality. You can do all those things. The proper way of understanding this is in the sense of distributions, because the Fourier transform of the sinc function exists. Sinc exists as induces a distribution. It's a fine function as far as integrating against a Schwartz function goes. All right? So the Fourier transform of the sinc function is a distribution. This has to be understood in the sense of equality of distributions, not in terms of sort of pointwise functions, but that gets a little extreme. All right? That gets a little extreme. You know, even religion has its limits. All right? Now, I'll say one more thing. One more thing. Like I said, I just wanted you to enjoy the ride a little bit. There's a little bit more of the ride to go. Next time, I'm going to talk about derivatives of distributions, how every distribution is differentiable. Removing that flaw from the classical theory of calculus, where not every function is differentiable, every distribution is differentiable, and we're going to get some formulas out of that. You know, why do we go through this? You know, again, you have probably seen these things derived in some tortured way in previous classes. All right? Well, like I say, things have moved on. This is the modern way of viewing Fourier transforms and how they work. And you should, as part of your education, want to know what the modern viewpoint is. You could build a radio out of vacuum tubes, but we don't teach that anymore. All right? We don't teach vacuum tube technology. All right? You should want to know, even if only to have sort of acquaintance that it's possible to do, you should want to know how the modern view of this is. And furthermore, as I say, it's not just that it's a good point of view, you can actually compute with it with confidence. I derived effortlessly these formulas, like the Fourier transform of 1 is delta, the Fourier transform of delta is 1. The derivations of those in the classical case are really quite involved and not at all, I think to my mind, convincing. All right, they get you the correct answer, but you know the cost of of torturing things to do that is quite high. All right, I see people wanting to get in. We're going to take a break. I know there was a question in the back you can ask me when we're on the way out. Okay. All right. See everybody.